Okay, so before we get started into the next section in Chapter 8, which is improper integrals, let's look at that example that we were looking at in class. The one that basically said the limit as x approaches infinity of 1 plus 2 over x to the x. So the reason that we'll need to use logs to evaluate these limits every once in a while is because you have this. It's raised to x. And finding the derivative of something raised to x is a little bit hard. So what we do is we take our base and we let this base equal y. So the idea is that if y is equal to 1 plus 2 over x, then we can rewrite our base, to the x, okay? So we take our base, or our function, and we call it y. So we rewrite this as y is equal to e to the ln of 1 plus 2 over x to the x. So I think you guys can agree with me that I didn't really change the problem. Okay, the function is still the same because e to the ln cancel each other out. But what this does help me do is it allows me to bring this x down from the exponent position. So now we end up with y equals e to the x ln of 1 plus 2 to the x. So here, by using logs, what we can do is we can kind of split up this problem. So we can find the limit of just this part right here. So then our answer will be e to something, whatever that something is. Since we needed to use the e to begin with, it's going to end up being in our answer at some point. So we basically rewrite this problem as the limit as x approaches infinity. And now we're just going to find the limit of x ln of 1 plus 2 over x. Okay. Now in order to use L'Hopital's rule, we need to put this into an indeterminate form. So these are our two parts. So basically I need one function on top and one function on the bottom. The easiest function to move to the bottom is this. So if I move this to down here, it's going to look like limit as x approaches infinity of ln of 1 plus 2 over x over 1 over x. Because if I move this to the bottom, it becomes x to the negative 1, and x to the negative 1 is the same thing as 1 over x. Now we can find the derivative, right? Now we can use L'Hopital's rule. So remember, the derivative of ln of x, of ln of something, is 1 over, actually let me just write it over here. So the limit as x approaches infinity. So the derivative of ln of something is 1 over that something times the derivative of that something, which ends up being negative 2 over x squared. And all of that is over the derivative of 1 over x, which is negative 1 over x squared. Now, algebraically, you guys should spot something right away, is that these two do cancel each other out, correct? Except for the 2. But the negative 1 cancels out, the x squareds cancel out, so we're left with the limit as x approaches infinity of 1 over 1 plus 2 over x times 2. So really this is the limit as x approaches infinity of 2 over 1 plus 2 over x. So now when we plug in our infinity, this is 2 over 1 plus 2 over infinity, which is 2 over 1 plus 0. So our final limit is 2. Now remember that this is the limit of this part right here. Since we had to use logs, our actual answer is going to be e to whatever we just got. So it's going to be e squared. Because don't forget that we actually used natural logs in order to solve this. Alright, so now we come into the next section. The next section here is on improper integrals. Now in our book, that is going to be section 8.3. I am going to use the notes from Calculus Maximus because he reviews everything a little bit nicer. And it's, I don't know, I just thought it was a little bit easier to understand. So, I am going to fly through some of these examples because of course you're going to have your calculators in front of you and you guys are going to be using your calculator to figure these out. I'm not going to pull out the calculator just because of timing. The video is going to be long. I'm going to break it up into two parts. Part 1 will be tonight. I'll try to do part 2 by tomorrow night. But let's get started. So we've studied definite integrals this year, and as you recall, they were pretty routine, right? They're easy and very, very courteous. But we did have to use a lot of integration techniques. So keep that in mind. Now we're going to study improper integrals. Basically, the idea of improper integrals is that you are integrating something from a set number to infinity. So improper integrals have some form a to infinity or negative infinity to b. But the idea is that you are trying to find the area under the curve to an infinite end. So let's start by getting your calculator warmed up and plugging these in. Now these are definite integrals. These are defined from 1 to 100. So really if you looked at the graph of 1 over x, which kind of looks like this, the idea is that we are finding the area from 1 to 100 of the function 1 over x. So you plug that in your calculator and you end up getting with 4.605. Do the same thing for the same function, but this time from 1 to 1,000, and obviously the area is going to do what? So from 1 to 1,000, obviously the area got bigger, so we're hoping that it should increase. And it does, to 6.907. And if you keep going, from 1 to 1,000,000 of that same exact function, in our calculator we end up with 13.815. So based on our values, what do you think the integral or the area of 1 over x from 1 to infinity will equal? Now we notice that it just keeps getting bigger and bigger and bigger. And it's not getting any closer to any one specific number. So in this case, for the function 1 over x, based on our calculator numbers, we can conclude that this is the area, okay, or the integral is going to equal infinity. Now if we go on to the second example of e to the negative x, this graph looks like this. And we'll talk about this little area in just a second. So from 1 to 100 of e to the negative x, if you plug that into your calculator, you'll get 0.3 0.367. And from 1 to 1,000 of the same exact function, you do get approximately 0.367. Now if you look at the rest of the numbers on both of these, you do notice that it does increase a little bit, but not a lot. So just a little side note that some functions, if we were to continue this from 1 to, I don't know, if we went to 10,000 of e to the negative x, our calculator will give us 0. But obviously that's not accurate, because if you think about it, there's still area, correct? From 1 to 100 it's 0.367. From 1 to 1,000 it's 0.367. So from 1 to 10,000 it should be a little bit more than 0.367, or approximately 0.367. But the calculator sometimes basically doesn't work for these types of integrals. So there's no way for you to check improper integrals using this method. This was just a, it works sometimes, of course, but not always. So this is not correct. In the calculator, basically, you can say broke, because the numbers are so small that it's basically telling us, well, it must be 0. Okay? But based on our information so far, what do you think the integral from 1 to infinity of e to the negative x dx equals? I would say it equals 0.367. So if we had to sketch the graph of both functions in the first quadrant, and we're going to shade the regions that are represented by both of these. So our first function of 1 over x looks a little like this. And from 1 to infinity, we're focused on this area over here. And then our second function, e to the negative x, it's a little different. Okay, first of all, it does cross through the y-axis, and from 1 to infinity kind of looks like this. So here we ended up, they look almost identical, but we obviously ended up with two completely different answers. And the reason for that is because this function right here moves toward, aka converges, towards the x-axis faster. Therefore, the area becomes finite. Okay, the idea is that yes, the area is infinitely growing, but it's getting so close that we can say that it's approaching this number. And then the further out you got to infinity, yes, it's increasing, but it's increasing by so little that we can give it an approximation. Now here it's increasing, but not fast enough. So by it growing steadily, by these big gaps, so here from 4 to 6 is 2 units, here from 7 to 13 is 5 units. So we don't know at what point it's gonna get close and close to the x-axis to give us this finite number. So why would these two integrals give such different results? It's basically because of the speed that a function approaches the x-axis. So the faster that function approaches in the x-axis, the more likely we're going to end up with a finite answer. The slower it approaches, we're going to end up with an infinite answer. So here this function converges, but here this function diverges, and we'll talk about these two terms in just a second. So very important that you remember these functions and how they look like and put them in your heads while we're doing a bunch of these examples. All right, so how do we deal with infinite intervals of integration? Well, we have a definition. Basically, the idea is that if the integral from a to b of f of x exists of every where b is greater than a, okay, so that means we're going from 1 to some big number, so a bigger number than 1, then the integral from a to infinity of f of x can be rewritten as the limit as b approaches infinity. And basically what we would do is just rewrite that infinite sign with b of f of x, and provided the limit exists as is finite, then we can solve it. Same thing here, if the integral from b to c of f of x exists where c is bigger than b, then the integral from negative infinity to some number c of f of x can be rewritten using the limit. So you notice that we use the negative infinity, so the limit is approaching negative infinity, and we rewrite negative infinity with b and solve it. So let's look at the next 3 examples. We'll do 2 of them together, and you guys will do the 3rd one on your own. But obviously these 3 are improper integrals. What gives it away? Because we have an infinite sign in the integrand. Okay, so the question is do these functions converge or do they diverge? So looking at this, 1 over x to the 3/2, this is very similar to the problem that we just did of 1 over x. But obviously it's x to the 1.5. So do you think that it's approaching the x-axis faster or slower than 1 over x? So here's what we're going to do. On the AP exam, if this was a problem that was in the free response, you're going to have to definitely use the definition and write it correctly. So the first thing we're going to do is we're going to rewrite it using the definition of limits. So the limit as b approaches, that's infinity, of the integral 1 to b, right, we're rewriting infinity with b, of 1 over x to the 3/2. Just to make it easy to integrate, I'm going to rewrite this as x to the negative 3/2. And now we're ready to integrate. Remember that limit is going to follow along. So what is the integral? What is the integral of x to the negative 3/2? Remember, you add 1 and then divide by that, so we end up with limit of b to the 1/2 of x to the negative 1/2 divided by negative 1/2 from b to 1. Let's simplify this, and we end up with negative 2, right? Flip the guy and multiply over the square root of x from b to 1. So here, the limit as b approaches infinity, let's plug in our b and take away our 1. So we have, I'm going to take out the negative 2 just to make it easy. So this is going to be 1 over square root of b minus 1 over square root of 1. So I took out the negative 2, and I was left with 1 over square root of x, and then I integrated from b to 1. or 1 to b. So now I have a function that I could plug in infinity into. So if I plugged in infinity into b, what I would end up with is -2 on the outside, 1 over the square root of infinity, which is 1 over infinity, and you guys know that that becomes 0, minus 1 over square root of 1, which is 1. So this is 0, so it's -2 of 0 minus 1, and that will give us the area under the curve of 2. So this guy converges to 2. Okay? Alright, let's do number 2 together. If you guys want to press pause and try this on your own before moving on. But just FYI, if this is not a free response and it's a multiple choice question, you really don't have to rewrite the function using b. You could just plug in infinity right from the beginning, but if it was free response and you don't use the definition, you will lose points. Alright, so let's pretend that this was a multiple choice question and you're just doing the side work. Then this is still going to be just the integral from 1 to infinity. I'm going to rewrite this as x to the -2 because it's easier to find the integrand of x to the -2. Now we integrate, so this becomes -x to the -1 from infinity to 1. And if I just rewrite this as -1 over x from infinity to 1, so this becomes -1 over infinity minus -1 over 1. And we know that -1 over infinity becomes 0. And -1 is just 1. And obviously this converges because we ended up with a finite answer. Alright, so you guys decide how you want to do part C. If you had to use the definition, you have to use the definition. You have to show all the work. You have to rewrite it as the limit and then go from there. If it's a multiple choice problem, you can just go ahead and integrate it like you've always done and use the definition of the fact that this equals 0. Now you'll notice at one point we will start using our old integration techniques and L'Hopital's rule in order to do this. It won't always work. Alright, so just FYI, when you guys do this, you should end up with an answer of 1/2. Alright, so here's a little fact that if A is greater than 0, so if you are starting from a number that is greater than 0 in the positive quadrant, going to infinity of 1 over x to some exponent p, it is always going to be convergent if p is greater than 1, and it's going to be divergent if p is less than or equal to 1. And we saw that in our first example. So when it was 1 over x, it was divergent, right? But when we had here 1 over x to the 3/2, it was convergent. These are called p-series integrals, and we're going to do more of these when we get into the series chapter, the last section. But they are called p-series. Now, in the p-series, we have a p-test. If a equals 1, and this is a special case, this is not always, okay, a has to equal 1, and p has to be greater than 1. So if that happens, then we have this special formula where we don't even have to do all of this math, but we can find out what our answer is and know that it converges to the number 1 over p minus 1. But this only works if a is 1 and the exponent is greater than 1. Okay? Now I like how he wrote this for those with fancy bathroom humor. It's interesting to note that the p-test, which is what this is right here, relies so heavily on the number 1. Makes sense? PP test. Alright, so look at this example. First of all, can we use the p-test? Yes, we can, because this is 1 and this is greater than 1. So we know that this is gonna, we're gonna use the p-series test because this is greater than 0, and the question is, this exponent is less than 1, so this function diverges, and where would it diverge to? Infinity. Because you're always only going to diverge to 2 spots. It's either infinity or negative infinity depending on which part of the graph you're looking at. And here we're looking at the infinite side, so it's divergent to infinity. Now next up, p here is greater than 1, so obviously this is going to converge. So since p is greater than 1 and our integral is starting at 1, we can use the p-test. So it's converging, and where is it converging to? It's converging to 1 over p, which is 1.1, minus 1. So this is 1 over 0.1, and we know 0.1 is 1 over 10. So 1 divided by 1 over 10 is 10. So it's converging to 10. Next up, you want to rewrite this so that you have a good idea of what your p exponent is going to be, right? So this is 1 to infinity of x to the 7. Obviously this is greater than 1. So it converges, and I can use this formula because we are starting at 1. So this is 1 over 7 minus 1, which is 1/6. Again, same thing here. You have to rewrite this, and we can take out the 3, and this is 1 over x to the 3/2. And I would let you guys do the math, but it does converge to 6. Okay. Last example for this video. Example 4. So obviously this is going to be an improper integral because of the infinity. And we are going to do this free response style. Okay, so we're going to use the definition and all. So the first thing we're going to do, since it's an improper integral, is we are going to rewrite this as the limit as b approaches negative infinity, right? From, so here our b is going to be at the bottom to 0 of this function. And I'm going to rewrite this just so that I can integrate it a little bit easier. 3 minus x to the negative 1/2 dx. Alright, I'm going to give you guys a minute. Do you remember how to integrate this thing? So this is what this section is going to do. We're basically going to be pulling out all of our integration techniques. Everything's going to come back. Partial fractions, tabular method, U substitution, integration by parts, the IBP, all of it. It's all coming back. Okay? So what are we going to use for this? Alright. So I'm going to let you guys know. It's going to be u substitution. So we're going to let u equal 3 minus x. So if u equals 3 minus x, if you remember, du is going to equal negative dx, right? But here, we don't have a negative dx, so we need to get rid of that negative 1. So here, negative du is going to be dx. So if we rewrite this, the limit as b approaches negative infinity from b to 0 of u to the negative half of negative du, right? And now we know how to integrate this. So I'm just going to keep going. I'm going to pull that negative out. So this is the limit as b approaches infinity of negative b to u of u to the negative 1/2 du. So can we integrate this? Of course we can. So when you integrate u to the negative 1/2, I'm just going to come over here. B to the infinity of negative, the integral of u to the negative 1/2 is going to be u to the 1/2 over 1/2 from b to 0. I'm going to rewrite this so that it's a little bit more proper. So I'm going to flip the guy and multiply. So this is going to be negative 2 over the square root of u from b to 0. Don't forget to plug in our, I don't know why I just brought that down. Sorry, apologize for that. That's going to be up here. I don't know why I brought that down, because it's positive. That shouldn't have come down. So here our limit from b to infinity of negative, let's plug in our b and our 0. So we get negative 2 square root of b minus negative 2 square root of 0. Oops. I forgot to do something, but honestly I'm trying to rush because my laptop is at 4% and I don't have my charger near me. So the one thing I forgot to do is plug u back in. Alright, so this is negative 2 square root of 3 minus x, right, from b to 0. So now we can plug in our b and our 0. So this is the limit as b approaches infinity of negative 2, 3 minus b minus negative 2, so I'm just going to change that to a plus, of 3 minus 0. So here our limit as b approaches infinity. Now I can plug in my infinity. So it's negative 2, 3 minus infinity, plus 2 of 3 minus 0, which is 3. So here, 3 minus infinity ends up giving us infinity. And I'm just going to let you know right now it diverges to infinity, and we'll talk about this in class. I need to stop this video right now. Alright, part 2, which is the rest of these notes, will be up sometime tomorrow, and then you're able to do the rest of that homework assignment, which will be due on Tuesday. Alright, good night.